Okay, what else? Now we'll talk about the processing of polymers. Okay, so typical processes for polymers are extrusion, injection molding, blow molding, and rotomolding. Okay, so this is the metal extrusion process. So this is the extrusion machine. This is an example extrusion machine, and we have here the hopper where the plastic pellets are feed into, and then because of this screw conveyor, then it is transported from this point to the exit point. Okay, so this is the hopper, the inlet, and the exit is we have a die. So just simply just the same as the metal extrusion process, that we have a die right here. So depending upon the shape of the die, that's gonna be the shape of um, the shape of the cross section. Okay, however, this is right here. This is plastic pellets. So there's a need for heaters. So right here we have a bond heater, so that heats up the machine so that it will fluidize the pellets, so that you can form it, or you can just push it through whatever sections right here, or whatever holes or cross-sectional shapes there is in this die. Okay, so that's the extrusion process. Okay, another one is injection molding. Okay, so right here we have an article for injection molding. So it's something like the same as the extrusion process, except that instead of having a die right here, instead of having a die, it's basically having a mold. So you are injecting the plastic right here into a mold. Okay, so that's the injection molding. Okay, and another one is blow molding. Okay, so for a blow molding, it's just simply something like an injection molding with a mold. So with this mold, except that there's an additional air that is introduced into this mold, or into this plastic and mold. Okay, so that's the process used for producing containers like this, bottles. Okay, and lastly, the rotomolding process. Okay, so here is an illustration for the rotomolding process. So uh, it's basically a container that's rotating. Okay, so here is the container, and the first step is to put a plastic pellets or plastic powders into that container. And then after that, the container is closed and it's being heated. So once it is heated, then of course the powder will turn into or it will soften. Okay, and if it is rotating, okay, so it is rotating, let's say in this vertical axis and in this axis, then somehow the centrifugal force will causes or will cause the plastic pellets to stick into the surface of the mold. Okay, so after that, so once it sticks into that surface, and it is cooled down, then what you'll get is a final shape that is something like this. Okay, so something like a blow molding, right? That it can create a hollow container, except that the process is entirely different. Okay, so this is common for large containers, large plastic containers. Okay, Okay, so such as this, maybe. Okay, going back. Okay, so the next one is heat treatment of steel. Now, heat treatment is a process. Okay, it is a process in which a metal is heated. Okay, it is heated to an elevated temperature from which it is cooled very rapidly. Okay, so it's about heating the metal and then cooling it. And in the process, the metal somehow gets stronger and harder. Okay, so let's check this link right here. And actually, this is a useful article where you can read the fundamentals of heat treatment. Okay, and right here it has this figure subjecting the metal into a higher temperature and then cooling it. Okay, so the principle is that there is actually a iron carbon phase diagram. Okay, so right here in this left figure, it is an iron carbon phase diagram. So in the horizontal axis, it says here a carbon content, and then in the vertical axis, that's the temperature in degrees C. Okay, so recall that for carbon steel, the range is around 0.17 to, I don't know, point 0.15 to 1.7, I guess. Um, so we are in this range. Okay, so let's say we are less than 1% right here. So you would notice that in this diagram, there's a lot of regions. Like for example, here, this is the region. What is this? This is perlite and ferrite, and right here, this is a ferrite region, and this one is an austenite and ferrite region, and we also have other regions. Okay, and if you recall in our topics in stainless steels about austenitic steels, stainless steels, or ferritic stainless steels, it all um, it all relates to this phase diagram. Okay, but this is just iron carbon phase diagram. Okay, so these are just regions or phases. That means that it has a different microstructures. Okay, so the point is that let's say we are in this let's say in this 0.5%, we are in this 0.5% carbon steel, and I mean a carbon steel that has a 0.5% carbon, and we are heating it up. Okay, so once heated it up, it's gonna be let's say we are heating it up to this range, to this phase, so it's gonna be austenitic. So that means that the the microstructure would be different from the ones that when it is in the room temperature, right? But it's gonna have an effect that if I'm going to heat it up and then rapidly cools it down, so somehow it changes the microstructures. Okay, so instead of going back to this original microstructure, it is it's gonna be different because of the rapid cooling. Okay, so somehow it's gonna retain this microstructures or alter some microstructures. All right, now let's talk about the mechanical fasteners. This mechanical fastener, it's a type of joining process, and they are classified into threaded or non-threaded. When I say threaded, the typical examples are bolts and screws, and for non-threaded, the typical examples are pins and also rivets. So right here, let's draw a bolt right here. Let's say this is a hexed bolt, so that means that the head has a hex shape, and this one, another one right here, a threaded fastener that's called a screw, and it's also a hex head. Okay, so my question is, what's the difference between a bolt and a screw? Okay, so having the same geometry, let's say having the same material. So what's the difference? Now the difference is that for bolt, it is intended to mate with a nut, but for screw, it is intended to mate with a top hole. So this top hole is basically a hole. So for example, this is our part, and this hole has an internal threads. So if the mating part is a top hole, then that's for a screw, and if the mating part is a nut, then that's a bolt. Now, actually, since they might have, I mean, some screws might have the same geometry as the bolt, then it is also possible that some screws um, may also accommodate to be mated with a nut. Okay, but the intention is actually, or the actual function of a bolt is to mate with a nut, and for a screw is to mate with a top hole. Okay, so right here, okay, right here um, in this figure, or in this website, there's different types of fasteners used in manufacturing, screws, bolts, and beyond. So right here we have a lot of screws. There are screws for wood, screws for metal, and we also have bolts right here, and this one is the nut. And for a nut, there's also a lot of types of nuts. Okay, so we have here the first one on top. That's a hexagonal nut, so meaning that it has a head, or a shape, a hexagonal shape. Okay, and there are also nuts with flanges. So right here, so we have a nut, but it has something like an increased area, or a flange area. And we also have something like this nut. I think this is a castellated nut. So if you have a bolt or a fastener or a pin, for example, a pin, or I think it's a bolt with a hole, and that pin to be inserted in the hole will fit through these slots. Okay, so that's one of the application of this type of nuts. And actually, there are still many other types. And this one, the last one, is a nut, but it's called a dome nut. So it's a nut, except that the other side, it's covered, and you can find these applications. It's I've also seen this in engine parts. And so it's a castellated, it's a dome nut. And for a washer, there's also many types of washers. Right here we have a flat washer, and also we have this type of washers, which has a uh, wider wider area as compared to this one, because there are types like, for example, fender type washers or SAE type washers. Okay, so uh, those are some of the types of the washers, and we also have this type of washers, which has a cut right here. It's actually a spring washers, spring lock washers. And we have washers like this one. um, I think this is a uh, external tooth washer, or uh, it's I mean, the use of these washers are actually, if there are vibrations, then of course this can help maintain the grip of the nut if you have this type of washers. And by the way, the function of the washer is to increase the bearing area. Okay, another one right here is we have a um, grades um, of fasteners or bolts. So we have grades. It's something like the grades in the steel, that if you have a higher grades, that means that you have a higher strength. So there's a grade in terms of SAE grades, and there is also a designation based on this metric. Let's say 5.8. So
this one, if you have a lower grade, then the typical application is for, let's say, door handles of the automotives, low stress brackets, and things like that. But if you have a higher grade, let's say 8.8, metric 8.8, or SAE grade 5, then that's used for bumpers, engine brackets, and things like that, right? So you would notice this 8.8 actually, or this metric designation, if you have this type of bolts, bolt head markings. It says here 8.8, and right here it's 10.9. So the higher the grades, that means that the stronger the bolt is. Okay, and for this one, for 10.9 or higher grades than the typically use, it says here grade 8, suspension, steering, brakes, motor, transmissions. Okay, so if you that's the typical applications for the bolts. And by the way, what this means is, for example, 8.8. That means that you have 80. I think approximately 800. 800 is the, let's say, 800 megapascals for the ultimate tensile strength, and 80% of that is the yield strength. Okay, for SAE grades marking, I think this is the markings at the head. So if you have much higher, or uh, higher number of lines right here, then that means that it is higher grades as compared to this one. It has only um, three three lines, or it says here hash marks. Okay, so um, you can read this article. Actually, it's very helpful also. Another one is, there's a lot of head types. So like this one, we have a hex. Well, I mean hex washer head, or this slotted pan, or Phillips. It's the plus signs, or it can have a Phillips plus a flat head. Okay, and what else? For machine screws. So this is what I was referring about. Although there are screws for other materials, okay, because it's the characteristic for non-metal. I think that's this pointed tip. But for mechanical parts, I think this is much common. Okay, so you have this type of screws. It's machine screws, and there's also a lot of heads. Like this one is probably the most common, the hex head, and there's also a head that intended for Allen wrench, okay, and things like that. Okay, and what else? So for blind rivets, now there are also applications wherein um, it's much economical, or it is much appropriate to use rivets rather than bolts. Okay, and a rivet, one type of rivet is the blind rivets, and it's composed of this assembly right there, or this part, the manual part and the body. So once they are assembled, it's it's actually holding the parts being joined. So let's say right here we have this part. Let's say this is part A, and then this is part B. So once it is being assembled, so it will hold the parts like this. All right, so going back to our slides, the next joining process that we'll talk about is the welding process. Welding is a process of fusing materials by melting the edges and often adding molten filler metal. So it's a joining process. Uh, it's actually a permanent joint. By the way, we haven't discussed this permanent versus non-permanent joint. Non-permanent. And difference between this permanent and non-permanent joint is that if you disassemble the parts, does it require to destroy the joint, or does it require to damage the parts? So whether the part or the joint, okay, part or the joint is destroyed, so that's called a permanent joint. So example of this is welding, and also the rivets. Rivets, I mean, based on this definition, because when you disassemble the parts, you are going to destroy the joint itself, the rivets. Okay, so in that definition, rivets is considered as a permanent joint. But for non-permanent, example of these are bolts and screws. Okay, so you don't have to destroy the parts, or you don't have to destroy the joints to disassemble the parts. Okay, so here in the welding process, it's a joining method whereby, let's say we have this part and then another part right here, and we are going to join these parts. Okay, so in order to join these parts, we have uh, to melt this. We have to melt this part and write this so that they can fuse together. Okay, so that's the welding process, and the welding the codes and standards for weldings. You can just check this American Welding Society because they develop codes and recommended practices and guides regarding the welding process. And right here we have this common welding process. We have the shielded metal arc, okay, SMAW, shielded metal arc welding, uh, typically referred to as the stick welding, the type of welding that uses electrodes. And this one is the gas tungsten arc welding. This one is gas metal arc welding, and there's still another. I mean, in our structures engineering course, we discussed about this FCAW. I mean, we only mentioned this flux core arc welding, and um, this one right here I included it here, the RCAcetylene welding. But I think um, this is probably more in brazing. Okay, anyway, for this shielded metal arc welding, it's commonly referred to as stick welding, and in operation, the electrode is attached to the electrode holder. So we have this electric machine equipment, right? And there's actually a setting right here wherein you can adjust the amperage and other other parameters. So right here, there's a positive terminal and there is a negative terminal. Okay, and um, there's there's one wire that's attached to the holder. Okay, so let's say this is the holder, and in that holder there's an electrode, and let's say this is the workpiece. So in the other terminal there is a clamp. Okay, so that when this electrode strikes the the material or the metal, then it conducts electricity, and thereby in this vicinity there's going to be a spark, or somehow because of that spark it's going to be high temperature and it's going to fuse the metal, or it's going to melt the metal. Okay, so in this links. So here we have this holder, this different types of holder. So the stick welding or the SMAW, this is it. This is the holder and this is the electrode. Now the other holders right here, they are um, for GMAW and JTAW, or MIG welding and TIG welding. Okay, in terms of the welding rods, there are actually many types of welding rods, and um, you would notice right here the number. Let's say 6011, and right here this is 6013 or 7013. And we have discussed this already in our structures engineering course, that the first two digits refers to the strength of the joint in KSI. So this is 60 KSI, and if you notice that for typical bars and plates, they're just A36, which has a 36 KSI um, strength, let's say yield strength. So this one 60 KSI. So the assumption, of course, that you have done the welded joint properly, And the third digit, I think that refers to the position. If it's overhead, or if it's in flat position or vertical or horizontal position. And the last digit refers to the flux. I think flux or coatings in the electrodes. Okay, another one is the gas tungsten arc welding. So tungsten inert gas. So there's an uh, let's say this is the equipment and this is the workpiece. Right here, there's a holder, and then um, there should be a clamp as well. And I think this has additional cylinder right here, and that the gas that's used is argon. So right here it says that inert gas used for shielding is typically argon. Okay, and for this gas metal arc welding or metal inert gas or MIG welding, um, it uses a continuous wire fed into the welding gun. So this is, for example, the welding machine. There's actually a spool of wire, a thin wire, and that wire actually goes to uh, it exits the handle right here. So let's say we have this handle and we have this workpiece. Right? So let's say this is the workpiece, and of course there's gonna be a clamp as well. So this wire actually exits in this handle, and there is additional cylinder right here, and that cylinder is a CO CO2 carbon dioxide, and that is used for shielding. Okay, and the last one that we'll talk about is the oxyacetylene welding, and it's a it's composed of these two tanks. One is a shorter tank but wider tank, and another one is thinner tank but taller. Okay, so there's one tank is called acetylene, and the other tank is oxygen. Okay, so the question is which one is the oxygen and which one is the acetylene? Okay, and this is a $1 million question, and the acetylene is this one, and the oxygen is this one. Okay, so they mix together in a torch, right? And that torch, there's actually a regulator. I mean, to control the mixture, right? To control the mixture of the flame, and also there must be there's a regulator right here, and also a gauge, so that it can monitor the proper pressure or the the proper operations. Okay, so last, no, I think this is not yet the last. This is second to the last joining process. We have the brazing and we have soldering, and basically the difference between welding, brazing, and soldering is in terms of temperature. So right here, if we have a temperature above 450 degrees C, that's what we call brazing, and below 450 degrees C is called soldering, which is typical in the electronic industries. And there is an upper limit, I think 1000 plus degrees C for welding. Okay, and this brazing and soldering, they uses a filler metal, which has a melting point lower than that of the base metal, right? So take note, the filler metal is lower, has a melting point lower than the base metal. Okay, and often for brazing and soldering, actually you can join the similar metals, whereas in welding, usually the joints or the metals being joined are similar metals. Okay, and lastly, this is the adhesive bonding. So we can also join materials by the use of adhesives. So adhesives, they they come in various forms or in several forms. It can be liquid, or it's available in liquid form, or in paste or solution or emulsion or powder or tape and film. So although they can be, uh, let's say, they, I'm not sure if it's less hassle than welding or brazing, but because you also need to prepare the surface to, to clean the joints before applying these adhesive ones. But I think it requires less components as compared to the weldings and the brazings. However, this adhesive material, the downside of this adhesive material is the temperature. So if the temperature is beyond the capability of the adhesive, then the joint will fail. Okay, so whereas in metals, it can withstand higher temperatures. Okay, and of course there's gonna be um, proper applications for adhesive. So should it be in shear, or should it be in tension or things like that? So we have to consider that as well in applying the bonds. All right, so that's all for this manufacturing process, and I hope you've learned a lot. And in the next video, we'll be discussing now our fourth topic, which is the load analysis, load stress analysis. All right, so see you in the next video.